Good morning. Good morning. What I want to be able to do is to look at se- resistors in parallel and in series parallel this morning. So again, you're not going to see what I'm doing, but you'll need to look at the video that says series parallel circuits. Parallel and series parallel circuits. Let me just get it right. Okay, one second. Let me just reconfirm quote. I don't want you saying that I gave you the wrong information and you will look at the wrong thing. Yes, it's resistors in parallel and series parallel. I repeat, resistors in parallel and series parallel circuits. Okay, thank you. Oh, sorry. Um, these things always go at the wrong time. So what I'm going to do now is just bring up my work that I want to do for this morning, and I'm hoping that I've made the screen big enough to be seen. Can I make it bold? Just make everything bold so it stands out. It's okay, I'm just trying to see if I can make everything bold so that it stands out. You don't have to emphasize anything but other than that. Okay. Okay, for you, 15, and let's go bold. So, okay, 1 second. Yes, it's okay. What I'm doing at the moment, I'm just trying to make this bold so that it comes up better on the camera, hopefully. Okay, so that's what I'm trying to do here at the moment. Um, okay, now let's close you down 1 second. Mhm. Okay, I think I'm getting there. It's just that nothing ever works the way you want it to work, does it? You think you got everything set up before you begin, and then suddenly your computer flicks over and it just drops everything out of sync. Okay, and mhm, just drops everything out of sync, and then you have the task of trying to put it back. Okay, what time? I think I'm getting there. I'm getting there slowly. I don't want to rush because the moment I begin to rush, then it gets even worse. And most of you will know what that's about. Okay. Especially when you want to go out on the town at night, on a Friday night, or so. And Saturday night. Don't worry, I was young once, a very long time ago. But in saying that, that doesn't mean to say that you ignore your work that you have to do, because this is your future. Believe me when I tell you that this is your future. What you do now, the training that you do now, will stand with you for life. It doesn't matter what the economic situation is or becomes, your training and education takes you anywhere. It allows you to diversify into other areas that you didn't even thought possible. Okay, let me just see what I've got now. And I think I'm on. Yep. Yeah, I think I'm there. Okay, let me just get you up to here. So. You are a light plane in the postorium. Okay, that's what we have for you. Okay, okay. Goodness me. Okay, let me just get lined up. Okay, I think I'm ready to go. Well, what I want to look at is resistors in parallel and series parallel. Resistors in parallel. Resistors are said to be connected together in parallel when both of their terminals are respectively connected to each terminal of the other resistor. Make sure I'm on that. Okay, yes. Now make sure that you look at this from your perspective and you read it as it is intended based upon what you know. So resistors in parallel. Resistors are said to be connected together in parallel when both of their terminals are respectively connected to each terminal. Now, what he's trying to say here is that the terminals, positive and negative terminals of the other resistor, okay, or resistors. Unlike the previous series resistor circuit, in a parallel resistor network, the circuit current can take more than one path. Okay, cancel. Okay, can take more than one path. So again, resistors in parallel and series parallel. Okay, and we look at resistors in parallel. Since there are a multiple paths for the supply current to flow through, the current is not the same at all points in a parallel circuit. However, the voltage drop across all of the resistors in a parallel resistive network is the same. resistors in parallel have a common voltage across them. And this is true for all parallel connected elements. So we can define a parallel resistive circuit as one where the resistors are connected to the same 2 points or nodes, and is identified by the fact that it has more than one current path connected to a common voltage source. In our parallel resistor example below, the voltage across resistor R1 equals the voltage across resistor R2, which equals the voltage across R3, and which equals the supply voltage. Therefore, for a parallel resistor network, this is given as VR1 equals VR2 equals VR3 equals VAB equals 12 volts. In the following resistors in parallel circuit, the resistors R1, R2, and R3 are all connected together in parallel between the 2 points A and B, as shown. And here is our parallel network, okay? R1, R2, R3 connected in parallel, okay? Across the supply voltage. Now remember, it doesn't matter which way your voltage comes in regards to this, it will still flow. But here we've used this as our potential current arrow indicating current flow, okay, for each resistor. In the previous series resistor network, we saw that the total resistance, you haven't done that yet, but you will do it in a bit, okay? So, and you should know what series resistors are by now anyway. In the previous series resistor network, we saw that the total resistance RT of the circuit was equal to the sum of all the individual resistors added together. For resistors in parallel, the equivalent circuit resistance RT is calculated differently. Here, the reciprocal 1 over R value of the individual resistances are all added together instead of the resistances themselves, with the inverse of the algebraic sum giving the equivalent resistance as shown. 1 over R is your reciprocal value, okay? Parallel resistors, and here we are. Parallel resistance equation, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over to the n, whatever value of resistors you may have in the circuit. Various parallel resistor networks, okay, and here they are, okay. Some of you may recognize something like this from Kirchhoff's. And here we have resistors in parallel. Example number 1, find the total resistance RT of the following resistors connected in a parallel network, okay. Here we have resistance total. We have R1 given a value of 200 ohms. R2 has a value of 470 ohms. R2 equals 220 ohms. You need to find the total resistance. And here's the process or the application that we apply. The total resistance RT across the two terminals A and B is calculated as 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Here are your values that you now put in. Okay. Now you can apply this method as you like. Okay. But I normally find the common denominator, but you can divide each one here, add them together, and you should get this value here. Okay. But I normally just find the common denominator into it and bring those values together, divide it. You then have to I believe you have to invert, but don't hold me to that. I'm just trying to remember from ages and ages ago. Okay. But make sure you understand the concept of parallel resistors. Now, make sure when you've looked at this that you understand how they've got this answer here, okay? And also how they've got this answer here, okay? I think I've put something like this already on my channel in regards to parallel resistance, but make sure you look it up and understand the concept. Okay. This method of reciprocal calculation can be used for calculating any number of individual resistances connected together within a single parallel network. If, however, there are only two individual resistors in parallel, then we can use a much simpler and quicker formula to find the total or equivalent resistance value RT and help reduce the reciprocal maps a little. This quicker method of calculating two resistors either equal or unequal connected together in parallel is given as RT equals R1 times R2 over R1 plus R2. We can also use a formula that allows us to calculate two resistors. This formula is shown below, okay, as I just mentioned here, okay. That's the formula that we're looking at. What the made you bigger? Okay, yes I did. Okay. Okay. And here, using our formula above for two resistors connected together in parallel, we can calculate, we can calculate the total resistance RT as RT equals 22 kilo ohms times 47 kilo ohms over 22 kilo ohms plus 47 kilo ohms equals 14,985 ohms or 15 kilo ohms. In our example above, the value of the combination was calculated as RT equals 15 kilo ohms, whereas the value of the smallest resistor is 22 kilo ohms, much higher. In other words, the equivalent resistance of a parallel network will always be less than the smallest individual resistor in the combination. So can my hand feel like it's going to sleep? Okay. Oh goodness me, okay. Let me just make sure that we have this all into view, okay. Okay, just making sure that it's in camera view and that I have everything as I would like it to be, okay? So just bear with me for a moment. Make sure that all the text is clear. Okay. Okay, thank you. I hope you found this useful and I will see you a little later. Bye bye.